Alright, so today we're going to do Taylor series in a day. It's a little bit cheating to call it Taylor series in a day because we've already seen a little bit of stuff about Taylor series. What class would make this lecture so much easier? Linear algebra. I know it's been too long since we've said that. And so because we don't have linear algebra, there's a limit to how deeply I want to go through Taylor series in several dimensions. I want to do enough just so you get the basics of how it's done. Fortunately, for most applications, a second-order Taylor series is all you need to know. Of course, on exams, I will potentially ask you for more than that. In terms of the calculus perspective, I'm not going to really write down more than the second order in several variables, unless we're in a very special situation. There's actually a trick that allows you to calculate multivariable Taylor series expansions in most situations that you need without knowing multivariable calculus. You get it for free if you know one variable Taylor series. And so what I want to do is I want to show you that trick and emphasize how you can use that trick. So let's start with one-dimensional Taylor. And so in general we have f of x is f of a plus f prime of a, x minus a, plus f double prime of a over 2 factorial x minus a squared plus dot dot dot. If we take a equals 0, then we have a Taylor series about the origin. We have a series expansion about the origin. Does it matter if a equals 0 or 5 or 23? No. We can always shift everything. What value would you like me to take a? If you could choose, what value would you like a to be? 2?
Just because, I don't know, I feel like something might happen with 1.
Well, you're saying it doesn't really matter what value of a I take, so which is going to lead to the cleanest formula? 0. Right? We'll expand things about the origin. Now again, you expand about where the action is happening. If I care about the point 2, we would expand about 2. If I care about the point 13, I would expand about 13. It'll keep things a little bit simpler if I do it about the origin. At a equals 0, I get f of x is f of 0 plus f prime of 0 x plus f double prime of 0 over 2 factorial plus, x squared plus dot dot dot. And in general, it'll be the sum, n goes from 0 to infinity, of fn of 0 over n factorial x to the n, where this means take n derivatives. What's the first thing you should worry about now? So I've just written down this series. What should you worry about? So we've got this series. What's your first thought when you see a series now? Does it converge or diverge? For which values of x will converge or diverge? Can somebody give me a value of x where this will converge? 0. No matter what things are, as long as you take x equals 0, it's fine. If x is not 0, it's not clear whether or not it will converge. And then it's also not clear, will it converge to the original function? So in fact, Taylor series do not have to converge to the original function except at the point you're expanding. And really, that's not a major accomplishment, because if you look at how you define it, well, I define it to equal my function at 0. Yeah, well, not surprisingly, it equals my function at 0. Does it equal my function anywhere else? How close is it anywhere else? So we'll see later today an example of a function where they only equal at the origin, but they are close everywhere. So then the question is, how rapidly are the derivatives growing? If the derivatives are dying, we know x to the n over n factorial converges for all x. So long as the derivatives aren't growing too fast, there's a good chance this will converge. So we're going to look at the truncated Taylor series. Tn, I'll call it Tnf of x, will be f of 0 plus f prime of 0 times x plus dot 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 plus the nth derivative at 0 over n factorial x to the n. So this is the nth Taylor series, the nth order Taylor series of f about x equals 0. Okay, so the question is, how good of a job does this do approximating the original function? What's the simplest point to look at? So what would be the simplest point to look at? So I want to compare these two. I want to compare this to the original function. What's a good point to check? $17.90 something, because that when Williams was founded. What's a good point to check? Yes.
I don't understand what we're comparing to.
Well, I'm saying that this is a really good approximation to my function f of x. And this is the Taylor series expansion of f at about the point x equals 0. So what point do you think I should check this against the original function? 0. So let's check. What's the value of the Taylor series at 0? This is just going to be, so if I put in x equals 0, I just get f of 0. All right, that equals the original value of the function. That's good. Let's take the derivative of the Taylor series. So if I take the derivative, t and f prime of x, we only have one variable, so I can use the prime notation again. What's the derivative of f of 0? What's the derivative of f of 0 with respect to x? 0. It's a constant. What's the derivative of f prime of 0 times x? F prime of 0. What's the derivative of f double prime of 0 over 2 factorial times x squared? I'm sorry? F double prime of 0. I want to write it a little bit differently. I want to write it as f double prime of 0 times 2 over 2 factorial times x. Because when I take the derivative of x squared, I get 2x. And if I continue all the way to the end, I'll get plus fn of 0 times n over n factorial x to the n minus 1. So that's the derivative of the function. So we saw at the origin, the Taylor series at 0 equals the function at 0. Let's now look at the value of the derivative at 0. What's the value of the derivative at 0? What will that be?
F prime of 0?
F prime of 0. So not only does my Taylor series at 0 equal the function, but its derivative at 0 equals the derivative of the function. And now let's take the second derivative, t and f double prime of x. What's the derivative of f prime of 0?
0.
0. It's a constant. F double prime of 0 times 2 over 2 factorial times x. What do I get? What's this piece going to give us? When I take the derivative, so I'm taking the derivative of this with respect to x. So what do I get?
Just f double prime.
I just get f double prime. I get f double prime times 2 times 1 over 2 factorial. 2 times 1 is 2 factorial. Now you can begin to see why we have all these factorials down here. As we take the derivatives, they're going to perfectly cancel. So we get f double prime of 0 plus, we then have f triple prime of 0, 3 times 2 over 3 factorial x, all the way to fn, we'll have an at 0 times n minus 1 over n factorial x to the n minus 2. And so if you keep going down, you'll see if we take the first n derivatives, they'll all match up. So the way to look at the nth order Taylor series is I'm looking for a polynomial of degree n such that the value of my polynomial equals the value of the function at the origin. The derivative of the polynomial at the origin equals the derivative of my function. The second derivatives are the same. The third derivatives are the same. I'm going to force the first n derivatives to be the same. I know in one of the sections people knew what the rate of change of the acceleration was called. Is it a jerk? Okay, so we're forcing the function to be, you're at the same place. You have the same initial speed, the same initial acceleration, the same jerk, and I don't know what the terminology is beyond that. If all of these things are the same, should you agree for a while? Should you be close to each other? That's the whole purpose of Taylor series. It's to replace a complicated function with a simpler one. And so here, this is the key relation. This is the Taylor series of order n about the point 0. And it's going to agree with my original function in many ways at the origin. And the hope is I'm using local information at the origin to get an approximation that should be pretty good in some interval. Okay? We will talk a little bit later today about how good. And this is where we will use one of my favorite theorems from calculus, the mean value theorem. Where did we use the mean value theorem up the wazoo earlier this semester? I told you this lecture could have been subtitled "The One with the Mean Value Theorem" and Homage to Friends. Not quite double integration. Fundamental theorem of calculus. You know, that was always the mean value theorem. We used the mean value theorem to show the upper sums and the lower sums were close, and then we used the mean value theorem to show that we could write the area as a telescoping sum. So we used the mean value theorem twice. The mean value theorem is extremely powerful. If you want, think of the mean value theorem as a poor man's version of Taylor series, where the mean value theorem only allows you to go to a linear term, but it doesn't evaluate it at the origin. It evaluates it at some unknown point. So the mean value theorem is wonderful. There's a lot of things it allows you to do, but you don't know where you evaluate the function to get equality. It just says there's some point C, such that if you evaluate at C, you get an equality. Well, that's great that there's some point. I want to know what that point is. Mean value theorem can't help you. So instead, the advantage of using something like this is I know where to evaluate everything. I can build this polynomial. The problem is it's no longer exact. And then we need to do some kind of analysis to determine how close it is. Okay, bless you. Any questions about this so far? Okay, so this is one variable Taylor series, and we'll see later that for most things we need in multi, that's all we need. I thought it would be fun to see a little bit of a movie or an online demonstration of just how well Taylor series can do. So, can anybody identify this function? Yeah. Either you can notice that this looks a lot like the cosine function, or you can see up there that I'm plotting the function cosine. Either one is fine. So Mathematica allows you to manipulate a bunch of things. I can manipulate what my starting point is. I can manipulate how many terms I have in my Taylor series approximation, and I can manipulate how much I zoom in and out. So for instance, I'm plotting from minus c to c. If I go like this, I will zoom out and you'll see more cycles, or I could really zoom in. You get freedom. If you want, you can play like the bouncing ball and follow the ball as it goes up and down. Lots of nice stuff you can do. The real fun thing is to increase the number of terms in my Taylor series approximation. So I'm trying to find the Taylor series approximation for cosine at the origin. And this is giving me the number of terms, and I have one term. And this purplish line is my first order Taylor series expansion. So it's basically the line y equals 1 plus 0x. And let's see how good of a job that does. So if I zoom in, this is a pretty small range, going from negative 0.06 to positive 0.06. It's not a horrible fit. This is the best line approximation. If you want to change your point as to where you're at, well, not surprisingly, the slope of the line changes. I was off by a little bit in terms of where I wanted x to be. You're right at that intermediate point where I get this slope. So anyways, I'll put it back at the origin. I'm now going to increase by 1, and here's my best second order approximation. Good fit or bad fit? That is not a bad fit of cosine with just a parabola. Now, of course, I can zoom out. Oh, I'm sorry, this is zooming in, yes. Let's zoom out a little bit. All right, are you surprised that it's not doing a good job as we get further and further away? Why not? Yes.
Because you can't make it go up once it's going down.
Yeah, once the parabola decides to go down, it's down. You know, this is like boxing. You have no chance of getting back up. It's a knockout. Okay? What about cosine? What do we know about cosine? Oscillates between -1 and 1. So for this, I've got some polynomial in x, some quadratic. Once it's down, it's never coming back up, so I can't be good forever. Well, I'm not going to want too large of a region. I can always assume my x for cosine is between -pi and pi. So I only need to have a good fit in that window. Do you think it would help if I went to a third order Taylor series expansion? Do you think I'd get a better fit? How many people say better fit? More the better, right? All right. So let's see if we get a better fit if I go up to 3 terms. No improvement. Why was there no improvement? Kind of sad, isn't it? Didn't get better. What kind of function is cosine? I'm sorry, I think I heard. It's an even function. Cosine of x is cosine of negative x. It turns out that if you have the Taylor series of an even function, you're only going to have even powers of x. If you have the Taylor series of an odd function, you're only going to have odd powers. So really, there's nothing that's gained by going to a third order Taylor series for cosine, because cosine is even. The third derivative of cosine at 0 is actually going to be 0. I'm not going to gain any information. What do you think I should do to get more information?
You bring it to the fourth.
Bring it to the fourth order. So let's go up to the fourth order. All right? And so, I'll zoom in a little bit. And here, it's not horrible. I'm a little bit more than 1.5, and I'm doing a pretty good job. Okay. If I zoom out a little bit, it's not so good. But we understand why it can't be so good, because this is going to be a quartic. Eventually, it's going to be going off to plus infinity because it's a positive term. Will I do anything by going up to the 5th order? 6th order? Hopefully. Here's the 6th order. Here's the 7th order. 8th order. 9th order. 10th order. I'm sorry, I guess I'm on the 14th order. I can't count. 16th order. So, essentially, with the 16th order, if you're starting from here and going all the way to here, you've got a full cycle of cosine. I can't even tell the difference anymore. The fit is this good. And in fact, I don't think I need to go all the way up to the 16th order. I could go down a little bit. 14th, 12th, even the 10th order. Okay, 8th order is pushing it a little bit, I think. It's really closest to whether or not 8th has completely captured everything. I'm missing just a little bit down there. But by the 10th order, it's essentially a perfect fit. This is amazing. You can approximate a very complicated function like cosine extremely well with a polynomial degree 10. In fact, half the coefficients are going to be 0. So that means you only need to store 5 values, these coefficients, and then you can build up cosine to incredible accuracy. I had mentioned that not all functions are well given by their Taylor series or their convergence issues. Here is the function e to the negative 1 over x squared if x is not equal to 0. What's the problem if x equals 0? You'd be dividing by 0. We're not allowed to do that. Well, we just defined the function to be 0 when x equals 0. If you think about it, x squared is always non-negative. If I plug in something getting very, very small, I have e to the negative 1 over very small. That's e to the negative really large. E to the negative really large is essentially 0. So you just define the function to be 0. All right, as I get away from the origin, what does the function seem to be approaching? 1. Well, if you think about this, if you put in a large number for x, 1 over x squared is a really small number. E to the negative really small is essentially 1 over e to the 0, which is 1. So the function should be approaching 1. And now we can play the same game as before. I can zoom in. This is plotting it from -10 to 10. Let's zoom in. We'll zoom in a little bit more. what do you notice near the origin?
Flattens out.
It's what?
It flattens out.
It flattens out. I mean, this is extremely flat. And this is kind of what you would expect. If you look at e to the negative 1 over x squared, if x is really small, let's say x is 1/10, you get e to the negative 100. If x is 1 over 100, you get e to the negative 10,000. This becomes extremely small. I stopped calling, so here, well, it's quickly already at 10 to the negative 11. It's beyond what mathematics is really able to show us. It's basically telling us it's 0, okay, we're impressed, it's 0. There's really no point in zooming in any further. It is flat. This is a function, and we talked about this earlier as an extra credit problem using L'Hopital's rule and the definition of the derivative. If you calculate the derivative of this function at the origin, it's 0. If you calculate the second derivative at the origin, it's 0. The third derivative at the origin, it's 0. All of the derivatives of this function at the origin is 0. So if you take that and you try to build the Taylor series, the only series you can build is the function that's identically 0. And so this function is only 0 at the origin. As you start moving far and far away from the origin, you'll see it's clearly non-zero. Your Taylor series, no matter how many terms you take, is never going to converge to this function except at the origin. You're always going to miss everywhere. And you're never going to get better the more terms you take. The purpose of this is to just show you that it gets very hard if you work with general functions. Most functions that we work with are nice, but there are a couple of functions that have disastrously complicated Taylor series. This is similar to how we had to be very careful about what it means to take the derivative of a function. We had to look at all those Kamm-Taylor paths. And this is why real analysis is such a hard subject, because you have to handle stuff like this. Okay. There is another way to look at the danger of this. If I take that function, I can add that function to this, and I'm not going to change any of the Taylor coefficients. So two different functions can have the same Taylor series. Another way of saying this is, if I give you a Taylor series, it does not uniquely specify the function. That's quite annoying. So the way you should leave this is, Taylor series are a great way to approximate a complicated function with a simpler function. The more terms you take, typically the better you do. And depending on how much you know about the differentiability of the function, you can actually even quantify how good of a job you're doing. Yes?
If you take a non-zero a with that function, can you get there?
The one we talked about a moment ago?
Yes.
Yes.
Okay.
It's the issue is trying to figure out what's going on at the origin. Away from the origin, the function's actually nice. But at the origin, the function is one of the 10 worst functions in analysis.
And if you took that non-zero a, when you approximate it, could you approximate?
That's a great question as to, could you then use that to approximate what's going on at 0?
Yeah.
I have never tried that. I believe the answer is no. It's a great extra credit question to see how far can you push that. My feeling is things would break down if you tried to push it, and that when you do the calculations, there'll be a natural barrier. If you take a Taylor series at x equals a, you'll be okay as long as you're in the interval 0 to 2a. When you try to go beyond that, you then hit that threshold of 1 over x squared, and then all hell breaks loose. Okay? Other questions about this? Alright, so what I'm going to do now is let's calculate some Taylor approximations. So if I give you any finite polynomial, the polynomial is just its Taylor series approximation. So I'll let you do that as an exercise. If I give you a quadratic, its degree 2 Taylor series is just going to be itself. Let's take something more interesting. Any thoughts as to what would be a good function?
ln(x).
I'm sorry?
ln(x).
Okay. Because you said it like that, you primed me to write it the way you want. Alright, we'll do ln of x, not ln of x. If I try to do this, where do you want a Taylor expanded about? What point do we normally like to expand about? 0. The problem is, what's the natural log of 0? Not natural log of e is 1. What's the natural log of 0? Doesn't exist. It's negative infinity. The natural log of 1 over e is minus 1. The natural log of 1 over e squared is minus 2. The natural log of 1 over e cubed is minus 3. This is going off to minus infinity. So what this tells us is we don't want to expand this about 0. Or if we do want to expand it about 0, we're not allowed to. One way to fix this is I can write the natural log of 1 minus x. And now what value would you like to take for x? 0. Well, if we take x equals 0, now we get the natural log of 1. Everything is defined. And then we want to take and see what happens as x approaches 1. And maybe that's a good way to approximate what's going on. So let's calculate. What's f prime of x? So I have to take the derivative of the natural log of 1 over x. What is the derivative of that?
Negative 1 over, negative 1 over 1 minus x.
Excellent. And the reason we have a negative 1 is we have 1 over 1 minus x, and then the derivative of 1 minus x, which gives us a negative 1. So what's f prime of 0? Negative 1. All right. What's f double prime of x? We have negative 1, 1 minus x. A nicer way to write this is negative 1 minus x to the negative 1. And now I'll get negative times negative is positive, 1 minus x to the negative 2, and then I get another negative from this. So I have 3 negatives, so I get negative 1 minus x to the negative 2. What's f double prime of 0? All right, f triple prime of x. What will I get? Negative 2, 1 minus x to the negative 3. F triple prime of 0.
Doesn't it become positive?
Yeah,
when you
because
do
they're
minus
two.
Negative x.
Negative times negative 2 is positive 2. And I have the derivative of 1 minus x, which gives me
Okay.
all of them are going to be negatives. F triple prime of 0 is negative 2. But I'm actually going to write this as negative 2 factorial. 2 factorial is the same as 2. I've given this lecture a few times before. The fourth derivative, what will that be? It'll be negative 3 times 2, 1 minus x to the negative 4. And then the fourth derivative at 0 is going to be negative 3 factorial. Let's do one more. What would the fifth derivative be? It would be negative 4 times 3 times 2. Well, there's really a times 1 if you want to look at it. 1 minus x to the negative 5. The fifth derivative at 0 is negative 4 factorial. And we could keep going. What do you think the nth derivative at 0 is going to be? Not negative n factorial. N minus 1 factorial. It's shifted by 1 unit. So we get the nth Taylor series of f about the origin is going to be f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial x squared plus the nth derivative at 0 over n factorial x to the n. So what do we get? We get Tnf of x. What's f of 0? F of 0 is just the natural log of 1. Is this in the range of the camera? And so what are we going to get? Well, f of 0 is just 0. F prime of 0 is negative 1, so we get negative x. F double prime of 0 is negative 1 over 2 factorial. What's negative 1 over 2 factorial?
Negative 1/2.
Negative 1/2. So we get minus 1/2 x squared. The next one is negative 2 factorial over 3 factorial. Ooh, what's 2 factorial divided by 3 factorial?
1/3.
1/3. So we get minus 1/3 x cubed, minus dot 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 minus, and the last one we have is n minus 1 factorial over n factorial, which is just 1 over n. So there is the Taylor series expansion for the log of 1 minus x. As an aside, there's a really interesting value of x to take. Anybody know what would be a really interesting value of x to take? I'm sorry? Well, I'm looking at the log of 1 minus x. There's an interesting value. If I take x equals 1, I have the log of 0. That blows up. But there is an interesting choice of x. Any thoughts? Yeah?
An x that's like really close to 1, but not 1.
Right, so screw being really, well, if you take it really close to 1, you're really close to, and this gives you a good approximation for a number whose logarithm is close to 0. But I claim there's an interesting value of x to take. Not x near 1, x near... Well, if I take x in 2, I've got the log of a negative number. I can't take the log of a negative. If I take x equals negative 1, I get the log of 2. It turns out the log of 2 is the log of 1 minus 1. If I take x equals negative 1, I get 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6. That's actually a series expansion for the log of 2. And this series will convert. Did I make a mistake?
Log 1 plus 1.
Oh, sorry, that should be a plus. That would be bad. This is actually a series expansion for the log of 2. We haven't proved that this series converges. It's an alternating series and the terms are getting smaller. It's not too bad to show that this converges. But I don't really want to take that digression right now. But here is an expansion. I'm going to show you a nice trick. If I wanted to study the Taylor series of the log of 1 plus x rather than the log of 1 minus x, could I just repeat all of this as before? I'm sorry? Well, I mean, I'm just saying, have f of x equal the log of 1 plus x, take derivatives, evaluate derivatives, go through the whole process. I could go through the whole process. Or, what I could do is I could say, let's take this expansion and let's replace x with negative x. If I replace x with negative x, I just save myself a lot of time. And I actually get x minus 1/2 x squared plus 1/3 x cubed minus 1/4 x to the 4th. So this is take x to minus x in the log of 1 minus x. So if you can observe that, that's going to save you a lot of time. If not, just do the calculation again. Whenever you compute something, it's always nice to check and see, is the answer reasonable? When x is really small, when x equals 0, this is the log of 1, which is 0. Okay, good. My Taylor series, when x equals 0, agrees with my function. Imagine x is a small positive number. We have the log of 1 minus x. So if x is a small positive number, do you think the log of 1 minus x is greater than 0 or less than 0? What do you think? So taking the log of a number a little bit less than 1. Positive number or negative number? So if you don't know this, you do not know logs well enough. Okay? Logs are not supposed to be mysterious. The log of e is 1. The log of 1 is 0. It's falling down. So the log of a number less than 1 would be
Negative.
So if I take x to be a small positive number, I have the log of a number a little bit less than 1. My answer should be negative. Great! This is negative over here. If I take x to be a negative number, I've got now the log of 1 plus a little bit. I should have a number a little bit greater than 0. Great, I have that as well. So whenever you have formulas, it's nice to do quick, simple checks. Is this reasonable? And by looking at what's going on, I can get a sense of, is this reasonable? So for homework, I'm going to ask you to compute a couple of Taylor series expansions. But this is the general idea of how you would do it. You just take your derivatives very carefully, you evaluate them, and you put them all together. Okay. Any questions about this? What I want to do now is I want to talk about multivariable Taylor series expansions, why you don't want to do them, and how you can avoid them by knowing calculus. Okay? Everybody's comfortable with this? This is much better than what goes on. So I want to write down the one-dimensional formula and talk about how you would try to generalize it. And so we will review a lot of the concepts from the semester in doing this, which is one of the reasons why I like including it. So one dimension. F of x is f of 0 plus f prime of 0x plus 1/2 f double prime of 0x squared. In several dimensions, what the hell do? We can't use primes, so what's f prime going to become? Yes?
Partial derivative with respect to x.
Just with respect to x? So now we have a function of maybe 2, 3, 4, maybe n dimensions.
Well, prime of x would be the partial for x.
Right, but I need to figure out how to replace f prime if I have a function of several variables. So what should f prime become? You're on the right track.
The gradient.
The gradient. So if I have n dimensions, I think I have maybe f of x, y. I'll just do 3 variables just for simplicity. Okay? Yes, this is simplicity. F of 0, 0, 0, plus the gradient of f at 0, 0, 0. Uh-oh. So I should be replacing x now with x, y, z. I can't just multiply 2 vectors, can I? I need to get numbers. How can I get a number from 2 vectors? Dot product. So if I evaluate the gradient at 0, 0, 0, I get a vector. I can dot that vector with x, y, z with how much I've moved. Now things get worse. And you'll see why we're only going to do second order Taylor in several variables. What comes next? The double gradient. The gradient's gradient. So this is called the Jacobian. The next one is called the Hessian. It's actually a matrix. Beyond a matrix comes a tensor, and then beyond that, it's, roll up your hands, head for the hills. Okay? So we have the Hessian. It is a matrix. So the ijth entry is the second derivative of f with respect to xi with respect to xj. What do I have to worry about? Whenever you see things like this notationally, what do you have to remember? I'm sorry?
Can't divide by 0.
We can't divide by 0, but what does this mean? Am I taking the derivative first with respect to xj and then with respect to xi? Or first with respect to xi and then with respect to xj? You always have to remember which way is it. Fortunately, if your second derivatives exist and are continuous, the two of them are the same. So this equals d squared f dxj dxi if second derivatives are continuous. This is the matrix elements. We have to get a number from this. And it turns out the way you do this is you have to do some kind of matrix operations. You take the vector and you write it as a column vector here, a row vector here. Take this matrix acting on this, and then this is essentially giving you a dot product. If you want, if there are any questions about this on an exam, if you just parrot this and write this down, that will be full credit. Because at this point, what do you really need? Yeah. This is where you really need linear algebra. And in fact, this allows us to come up with really good rules for finding maximum and minimum. Because what goes on is, imagine we have a function whose gradient vanishes at a point, and we're at a critical point. Then near that critical point, my function looks like a constant plus 0 plus some kind of matrix form like this. And this is the generalization of a parabola. This is like the three-dimensional version of a parabola. And then depending on the structure of this matrix, you can tell is it a parabola going up or a parabola going down. Or maybe some kind of mixed region where it's going up in some directions and down in others. I really don't want to get too deeply into that because you have not done linear algebra. I want you to be aware that this exists so that if you do take linear algebra, you can now see how it's done. I also want you to be convinced that you do not want to do this. Okay, is everybody convinced that this is not a fun way to spend the last week of the semester? I'm going to show you how to bypass this. So let's say I give you the log of 1 minus x times y. And I want to find the third order Taylor series. Let's do the sixth order Taylor series expansion of this. Okay? I want the sixth order Taylor series expansion. One of the reasons this is such a hard problem is I've only told you how to get up to... Oh, actually, this is actually wrong even. What did I forget here? I forgot... I'm sorry?
Squared?
Not squared. The x squared actually breaks like this.
Oh, okay.
Coefficient.
I forgot the coefficient. I forgot the 1/2 or the 1 over 2 factorial. So one of the reasons the sixth order Taylor series is going to be so hard is I haven't even told you what the next terms are. How do you deal with x cubed? How do you deal with x to the 4th? Here's a way to bypass this. I have the log of 1 minus xy, and I want to figure out what does that equal. Well, I know what the log of 1 minus u is. This is just negative u minus u squared over 2 minus u cubed over 3 minus u to the 4th over 4. What should I do? Let's plug in.
XY.
Yeah. Just set u equal to xy. And now we get the log of 1 minus u is negative xy minus x squared y squared over 2 minus x cubed y cubed over 3 minus x to the 4th y to the 4th over 4. If I want the sixth order Taylor series, where do I cut it off? Would this term survive for the sixth order Taylor series? Well, let's think. How many x's and y's do we have here? I have 4 x's, 4 y's for a total of how many?
8.
So this would be a degree 8 term, or an order 8 term. Order 8. What would the order of this term be? 6, 4, and 2. So if I only wanted a degree 6 expansion, this is a degree 8 term. I wouldn't need it. So the sixth order expansion is the log of 1 minus xy is negative xy minus x squared y squared over 2 minus x cubed y cubed over 3. And that's it. So as long as I give you something nice, where you can just say, I can regard this as a function of one variable, and then just let that variable be my combination, I'm fine. Okay? And so in a situation like this, I can bypass having to calculate this. I am assuming nobody wants to calculate expansions like this, do matrices like this, and do products like this on the exam. If you can just remember how to do it like this, if I give you any of these problems, this is a subjunctive. But it's not really a subjunctive because you should figure out that a problem like this would be emerging. Then if you can do it like this, you will get the problem right. Okay? Okay? So if you can master this, you will be able to do any expansion. You need to at least know how to state the formula for 2 dimensions and higher, but you do not need to know how to use it. I do not feel that is an appropriate requirement for a class that does not know linear algebra. I think it's a nice way to motivate why you care about linear algebra. You know, we saw in the streaming video lecture how useful stuff like this can be. This is not just, I got to fill up the course, we've got 1 more week, let me put in a topic. Is there anybody here who has not watched streaming video and is willing to admit it? You've never seen anything streaming on the internet?
Oh, no. It's not
Okay.
the one from the work.
Okay. That was the first time you've ever... Oh, no, I won't ask that in public. But, I'm assuming in the 21st century, almost everybody, if not everybody, has watched some kind of streaming video, something on the internet. And I'm assuming you don't like it when it hangs. You want to transmit information very quickly. It turns out Taylor series are good, but there's better things than Taylor series. That's fine. In the first course, we're not going to get to the optimal state of the art, but we can get to what are the key ideas being used. This is not needlessly filling up the material. We need something to talk about. This has enormous applications. Instead of transmitting the whole function, I can transmit a couple of coefficients, and then you can reconstruct the function on your end. That's why this is so useful. If I want, and you saw this in the streaming video, if I plot my function at lots of different points, not surprisingly, I can do a really good job. But it's also expensive and time-consuming. You then have a lot of information to transmit. If I can transmit just a few numbers, and then you can use that to build it up, that's much better. Is your computer... I'm trying to think of the right phrases. Do you have a powerful computer or a weak computer? Powerful. You have enormous amounts of computational power. So, by all means, use it. You don't have to transmit every pixel because your computer is fast enough, your phone is fast enough now to be able to do these computations in real time. And because you have that much processing power, you can afford to transmit less. That's why we care so much about these Taylor series. Okay? Do you want to do another example? Sure? Okay. So, basically, we have 1 minute left. Yes, let's do one more example. So whoever reset that clock did not do a good job resetting it. All right. And let's erase this monstrosity because nobody likes this monstrosity. So if you do work, you'll see the cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus double count. Let's do the cosine of xy squared. What does this equal? Well, the cosine of u is 1 minus u squared over 2 factorial plus u to the 4th over 4 factorial minus u to the 6th over 6 factorial. So the cosine of xy squared is 1 minus x squared y to the 4th over 2 factorial plus x cubed y to the 6th over 4 factorial minus x to the 4th y to the 8th over 6 factorial. If I want the second order Taylor series, what's the second order Taylor series? No, it does exist. Second order Taylor is what? I take all terms where the sum of the x and y powers is at most 2. What would the second order Taylor series be?
1.
1. Alright. Third order. 1. Fourth order. Fifth order. Sixth order.
1 minus x.
Alright, 1 minus x squared y to the 4th over 2. Seventh order, 8th order, no change. Ninth order, I would now add this term. Okay? So again, once you know one-dimensional Taylor series, if your functions are of a nice form, you can calculate the higher ones without too much trouble. Yes?
Why is it 13 and 4 precisely not x equal 4 to 8?
Which one? This one?
Oh. Is that,
I'm just replacing u with xy squared.
so why
Oh wait, did I do something wrong? Oh, sorry, yes. Thank you, you're right. I did this wrong. You're right. You're absolutely right. So this should be to the 4th power. So it should be x to the 4th, y to the 8th, and then this should be x to the 6th, y to the 12th. Thank you. So in fact, the 6th order Taylor series is still this. But the 7th, 8th, 9th, 10th, all the way up to the 11th order Taylor series is still this. You're absolutely correct. Okay. All right. Enjoy the good weather.